Hello everyone and welcome to General Chemistry 2 or Chem 152. This is lecture 8 on kinetics. We're going to learn about reaction rates and rate laws. This is the first lecture in Unit 2 and it covers OpenStax sections 17.1 and 17.3. Let's begin by discussing chemical kinetics. So when we're talking about kinetics here, we are referring to how fast a reaction will occur. So we're going to look first at reaction rate. Reaction rate can be measured as the change in the amount of either a reactant or a product as the reaction proceeds over time. So suppose we have some reaction going from A to B, so some general reactant A being converted into some general or generic product B here. So we can describe the reaction rate. So again, here, this is a reaction rate, and it's measured by the change in the amount of either a reactant, in this case a reactant, over time. So it's kind of just like speed, right? Speed, when you measure someone's speed or the velocity, right, we think of miles per hour. So it's the change in their distance divided by time. A reaction rate is very similar, but it's the change in the amount divided by time. Here you'll see that we have brackets. So brackets stand for concentration. So this is the change in concentration of reactant A during time period T. Here we can see the Greek letter delta. Remember, delta meaning change. And then you'll notice this negative sign in front. The reason for this negative sign is that these rates themselves here, so a reaction rate should always be positive. We always think of reaction rates as being positive. But A here is a reactant, and this reactant is going to be consumed as product B is formed. So A's concentration is going to decrease over time. So delta A is going to be negative, and so we need this additional negative sign here to cancel out the negative from this term, making our rate positive. We can set up a similar equation here for the reaction rate of B, or the rate of B, where we say that delta B divided by delta T gives us the rate of B. So the change in concentration of product B divided by the change in time, or delta T. And here, again, this first expression has a negative sign because it is a reactant that is being consumed. So anytime you write the reaction rate for a reactant, you are going to want to put a negative sign in front here to cancel out the negative from this change being inherently negative. If you were to observe this and record this data, it might look a little something like this, where you have number of molecules or concentration, some sort of concentration value on the y-axis and time on the x-axis. So suppose we start with 40 molecules of A, our reactant, and none of B, the product. Here we can see that as molecules of reactant A are converted into molecules of product B, the concentration of A is decreasing over time, while the concentration of B is increasing over that same time period. Reaction rate can be monitored in a number of different ways. One way that is often used is spectrophotometry. So now this will only work if you have reactants and products that are clearly different colors. So one hypothetical example would be this. Here we have liquid bromine, Br2, which has this reddish brown color. And then our product, bromide, Br-, is clear, or it's colorless. So if you put Br2 in a reactant or a reaction vessel with HCOOH, it will eventually form bromide along with some hydrogen ions and carbon dioxide gas. And so we can see as the reaction proceeds over time, the solution loses its color. So we could monitor this with the spectrophotometer. Suppose we recorded the absorbance at 393 nanometers, which is where liquid bromine absorbs light. Over time, that absorbance would drop, and you could basically use that absorbance to determine the concentration of bromine over time, and you could use this then to determine the reaction rates. All right, now let's look at some actual data here. And let's think about average rates. So suppose I ran that reaction and I monitored it every 50 seconds. And so I can see then at time 0, we have a bromine concentration of 0.0120 molar. And then we record data every 50 seconds. We can see that the concentration of the bromine is decreasing over time. So a typical question you may be asked is, what's the average rate of disappearance of BR2 over the entire 400 seconds? Now, average rates are calculated the same way we would find the slope of a straight line. Keeping in mind here that the difference between the average rate versus the instantaneous rate, we are going to analyze this point right here a little bit more closely in a couple slides. But let's start by finding the average rate of consumption of BR2. So as mentioned, they are calculated the same way we would find the slope of a straight line. So if we want to find the rate of BR2, or the average rate of consumption of BR2, we would just start, or we would use the last data point and the initial data point. So here we'll consider this we could call this our y2 and our y1. So if we think of a slope calculation, right, it's y2 minus y1 over x2 minus x1. So we can think of these concentration values as the y values and the time values as the x values. So here, our final concentration, we could consider this to be our y2. And our initial concentration would be the Y1. So we can see on top here, we have 0.00296 molar minus the 0.0120 molar. On the bottom, we have the x2 minus the x1. So x2 would be the final time value, 400 seconds, and x1 would be the initial time value, 0.0 seconds. Remember that since BR2 is a reactant, when we set up that initial rate equation where we say rate BR2 equals negative delta BR2 over delta T, so here that negative sign goes on the outside here, and then again notice that since Y2 is less than Y1, this difference in concentration is going to be negative, and so these two negatives will cancel each other out, which gives a rate of consumption of 2.26 times 10 to the negative fifth molar per second. So this is the average rate of consumption, or we could just say this is the average rate of BR2. It is 2.26 times 10 to the negative fifth molar per second. All right, what if we wanted to know the average rate of disappearance, and disappearance consumption generally mean the same thing here over the first 50 seconds. So instead of asking for the average rate over the total trial, we just want the first 50 seconds. This is calculated the same way, but now instead of making y2 and y1 at these two data points, we'll use these two data points instead. So we'll do 0.0101 molar minus the 0.0120 molar, and then 50 minus 0. Again, we got that negative sign on the outside since BR2 is a reactant which is being consumed. And we get an answer of 3.80 times 10 to the negative fifth molar per second. Now question, why is this rate larger than the rate over 400 seconds? I'd like you to think about this one. Why do you think it is that the BR2 is being consumed more quickly in the first 50 seconds than the average rate is? And we will address this later on today and a little more in the coming lectures. I would just like you to ponder this question for a moment. But I'm going to keep moving. Suppose you had a graph like this, which shows the concentration of bromine on the y-axis and time on the x-axis. That first calculation we did, the average rate of change of BR2 over the entire 400 seconds, we basically drew a line from the first data point to the last data point, and this gave us the average rate of change over the entire trial. We can also calculate instantaneous rates of change. So an instantaneous rate of change is calculated by drawing a tangent line. So if I wanted the instantaneous rate of change at t equals 0, so hopefully you are somewhat familiar with calculus. A tangent line is a line that basically it just touches the data point. So here it just touches t equals 0, and we draw a line that matches the slope as the slope of this line is at t equals 0. So basically this blue line right here is giving us the instantaneous rate of change, or the slope, at t equals 0. And so this line should only touch the black line, our curve, right at t equals 0. So this is an approximation. If you want to get the actual value, you would want to do a little bit of calculus here. and then take a derivative. Here we're just estimating visually, and so I get a tangent line, which gives me the instantaneous rate of change of BR2 at t equals 0. I could also do this at t equals 400, so drawing a tangent line off this last data point right here. Now you may be asked questions to estimate these instantaneous rate of changes, and how would you do this? Start by drawing that tangent line, so just estimate it to the best of your ability. Then you're going to estimate the slope of this tangent line. So here I've drawn a little triangle where this side of the triangle right here gives me the change in y, and this side of the triangle gives me the change in x. So what I could do then is I could do y2 minus y1. So y2 would be where this line ends. So I'm estimating this at around 0.0071, and then my y1 value would be right here at the top of this line. So here is my y line. So right here, this point is my y2, and then this point right here is my y1. On the bottom are my x values, or my time values. So I'm looking at this part of the triangle right here. This point right here would be my x2 value, which I'm estimating at around 109 seconds. And then right here is my x1 value, which is right on the axis 0. So I get negative 0.0071 minus 0.012 over 109 minus 0, giving me an instantaneous rate of change of 4.6 times 10 to the negative fifth. So this is a fast rate, much faster than the average and faster even than that rate over the first 50 seconds. If we were to look at the tangent line, or the instantaneous rate of change at 400 seconds, so we draw our tangent line, make a little triangle, so draw a vertical line down to estimate the change in y, and draw a horizontal line across here to estimate the change in x. And if we set this up, I'm going to do y2 minus y1. So here, starting with the y values, here's the change in y. So this point right here is my y2, which I'm estimating is somewhere around 0.0029. So that's this point right here. And then this right here would be my y1 value, which I'm estimating at around 0.0041. Then my change in x, my x2 would be where I end, which would actually be right here at 400 seconds, and x1 would be this point right here where I start. So here's my x2, here's my x1. The x1 to me looks to be around 243 seconds, so I would say 400 minus 243. This gives me an instantaneous rate of change of 7.6 times 10 to the negative 6, so the smallest rate we have seen. So notice then that the rate is fastest at the start and slowest at the end. So when you're pondering that question I asked, sorry, I'm backing up a little bit, right here, the rate is fastest at the start and slowest at the end. Why do you think this is? Again, we will explain this in further detail later in these slides and in the coming lectures. All right, so let's keep going. Now we're going to discuss reaction rates. So in a reaction, there are at least 3 different rates we can consider. First, there's the rate of the reaction itself. So this is just how many times per second the overall reaction will run. So this reaction, let's say this reaction runs, maybe every second there's 10 cycles of the reaction. So in every second, 10 molecules of A are converted to 10 molecules of B. Then we could say the rate of the reaction is 10 per second, so to speak. So the reaction itself has a rate defined as rate reaction. We could also analyze the rate that a reactant is consumed at and the rate that a product is formed, which we defined earlier. These two things right here, these are called rate expressions for A and B, and these rate expressions are going to be used to help us break down something called relative rates. So this graph here shows the change in concentrations over time for the reactant and products in the reaction. 2NH3 forms N2 plus 3H2. So we have one reactant, NH3, and 2 products, N2 and 3H2. The black line here represents NH3, and the red line represents N2, the blue line represents H2. So notice then, since NH3 is our reactant, it gets consumed, so its concentration decreases over time, whereas N2 and 3H2 are the products, so their concentrations increase over time. They're being produced. Now, the instantaneous rate of change was measured at t equals 500 seconds, so somewhere right around here. So the instantaneous rate of change was measured for each compound here, for the NH3, the N2, and the H2. The rate for NH3 is 1.94 times 10 to the negative 6 molar per second. For N2, it's 9.70 times 10 to the negative 7th. And for H2, it's 2.91 times 10 to the negative 6th. Question, what is the relationship or the ratio between these three rates? So I'm going to go ahead and pause the video and see if you can figure out what the relationship, or more specifically, what the ratio between these three rates is. Okay, hopefully you noticed then that these rates are actually directly related to the stoichiometric coefficients in the balanced chemical equation. Notice that N2 has the smallest rate, and N2 has a coefficient of 1. If you took N2's rate and multiplied it by 2, you would get NH3's rate. And then notice, N2 has a coefficient of 1, and NH3 has a coefficient of 2. If we look at N2 versus H2, if you took N2's rate and multiplied by 3, you would get H2's rate. N2 with a coefficient of 1 and H2 with a coefficient of 3. So the relative rates of each of these components here, the reactants and the products, are directly related by the stoichiometric coefficients. So the rates of change are directly related to the stoichiometric coefficients. All right, so let's look at this a little further. Again, one more time, the relative rates of reactants, products, and the overall reaction itself are related by stoichiometry. So if we had the generic expression 2C forms D, questions here are how many moles of C are consumed each time the reaction runs? Your answer here would be 2. How many moles of D are produced each time the reaction runs? The answer there, 1. So how many moles of C are consumed for each mole of D formed? 2 moles of C are consumed for each mole of D formed. Then what are the relative rates of C and D versus the reaction rate? We will answer these questions here in the coming slides. So let's start with these three questions. Will D increase twice as fast as C decreases, half as fast, or the same rate? So not three questions, but one question with three possible answers. Let's analyze the difference in the rate of change for D versus C. So consider starting with 10 moles of C and 0 moles of D, and we're going to pretend here that this reaction runs once per second. So after 1 second, the reaction runs through one time, and we have 2 moles of C are consumed and 1 mole of D is formed. So C's concentration would go from 10 to 8, D's would go from 0 to 1. Now another second goes by, one more cycle of the reaction runs, and we go down from 8 to 6 and up from 1 to 2, and we keep going with this until we end here, where after 5 seconds, the reaction has run 5 times, there's no C remaining, and there's 5 moles of D that have been produced. So we can calculate the rate of C by saying 0 minus 10 over 5 minus 0, which gives the rate of C as 2 moles per second, and then the rate of D would be 5 minus 0 over 5 minus 0. Where did I get these numbers from? Recall that change is typically calculated as final minus initial. So for C, its final concentration is 0 moles, its initial is 10, which is why these values are here. The time for both is 5 minus 0. And then for D, 5 minus 0. Final concentration of 5, initial concentration of 0. So we can see then that D will increase half as fast as C decreases the rate of D would actually match the rate of the reaction. We could say that the overall reaction rate is 1 mole per second. Since the reaction runs 1 time per second, D has a rate of 1 mole per second, and C has a rate of change of 2 moles per second. Again, these relative rates of the reactants, the products, and the reaction itself are related to stoichiometry. So from this, we can establish a stoichiometric ratio. So the relationship between the reaction rates of C and D are related by this stoichiometric ratio, where we can say the relative rate of C times 1 mole of D over 2 moles of C. So this is essentially a stoichiometric ratio, or a conversion factor from the balanced chemical equation, equals the relative rate of D. This can actually be simplified, and we can say then that rate C times 1/2 equals rate D. To make this a little more general, for a reaction AA, so here the little a refers to the coefficient, the big A is the identity of the reactant, and then on this side the little b is the coefficient, and the big B here is the identity of the product. So we can say then that the rate of consumption or formation of an individual reactant or product, so rate of consumption for a reactant, or rate A, is negative delta A over delta T. The rate of formation for a product would be rate B equals delta B over delta T. The rate of the overall reaction, or rate reaction, equals 1 over A rate A, 1 over B rate B. So remember that the overall rate of the reaction is related to the rates of the reactants and products. So we can say that 1 over A. Here, this little a again refers to the coefficient. So if, let me back up here just a second to the previous example that we were just working on, so we had some actual numbers. Recall here that in this example, the reaction itself, so each cycle of the reaction ran every 1 second, right? 1 second per cycle. So we could say then that the rate of the reaction itself was 1 mole per second. Notice that the reaction rates, or the rate of the reaction itself, matches the rate of D, because D has a coefficient of 1, whereas C's rate is twice as fast. So now if I go back to this slide here, rate reaction equals 1 over A rate A. Suppose that the reactant A had a coefficient of 1. This would then give you 1 over 1, meaning that the rate of reaction would be equal to the rate of consumption of A. Or if B had a coefficient of 1, then this would be 1 over 1, and we could say that rate reaction equals rate B. From this, we can get expressions for relative rates. So these things, basically, this slide right here is a very important slide to remember, and you can take this slide and apply it to any of the rate expressions, relative rates, reaction rate type problems you will see. Here, these two expressions give us the relative rates, or the rate expressions for a reactant and a product. Here, this relates the rate of the overall reaction to the reactants and the products. And here we can get expressions for those relative rates, where we can say that negative 1 over A over delta T equals 1 over B over delta T. So essentially, we set these two expressions. We took these expressions and subbed in these expressions and combined them to get this expression down here. And the last one states that rate A times B over A equals rate B. And so that comes from setting these two terms equal to one another and getting the constants, these coefficients on the same side. All right, so this has all been very general thus far, and it may have been a little bit confusing. Let's look at some actual example problems. Let's start with this one here. Write expressions to determine the rate of the following reaction based on the rate of consumption or formation of each reactant and product. Here we have the balanced chemical equation, CH4 plus 2O2 forms CO2 and 2H2O. Let's start by writing the rate reaction for CH4. So we can say then that the rate of the reaction equals negative delta CH4 over delta T. So notice that every time the reaction runs, so if one cycle of this reaction runs, 1 mole of CH4 would be consumed. So we would just have a 1 in front here. Also, since CH4 is a reactant being consumed, we need a negative sign here because reaction rates should always be positive. If we were to write this expression here for O2, we should recognize that it will similarly have a negative out front because O2 is a reactant being consumed, but you need a 1/2 in front. Notice that every time the reaction runs, so if one cycle of the reaction runs, 2 moles of O2 are consumed. So the O2 is actually being consumed twice as fast as the reaction rate itself. So we would then say that the rate of the reaction equals negative 1/2 delta O2 over delta T. If we write this for CO2, notice that it has the same coefficient as CH4, so we still just have a 1 out in front, but now CO2 is being produced, and so we don't need that negative sign. It would just be a positive delta CO2 over delta T. Since the reaction runs once, 1 mole of CO2 is produced. And finally, H2O. Notice that the H2O is now going to be similar to the O2. For every time this reaction runs, 2 moles of H2O are produced. So the reaction produces 2 moles of H2O every one time it runs. Or we could say for every 1 mole of H2O produced, reaction rate is half that. So we need a half out front here. But since H2O is being produced, the sign is positive. All right, now let's look at some more precise values or maybe some actual rates here. This question states, if the rate of consumption of HI is 5.0 times 10 to the negative third molar per second in the reaction below, what is the rate of formation of H2 in the same reaction? All right, so we've got a rate of consumption here for HI, and we're being asked to solve for the rate of formation of H2. So let's use some stoichiometry and set up a ratio. Using stoichiometry, we can see that the rate of formation of H2 is equal to half the rate of consumption of HI based on these coefficients, right? We have a coefficient of 2 here and 1 here. So we can say then that rate HI times 1 mole H2 over 2 moles HI equals rate H2. In other words, HI is being consumed twice as fast as H2 is being formed. So you can think about it whichever way makes more sense to you to think about it. You can say that the HI is being consumed twice as fast as H2 is being formed, or you could say that the rate of formation of H2 is half the rate of consumption of HI. Either way is going to work. Here, if I use this expression, I would plug in 5.0 times 10 to the negative third here. So 5.0 times 1/2 gives an answer of 2.5 times 10 to the negative third. So the rate of formation of H2 would be 2.5 times 10 to the negative third molar per second. All right, so this wraps up rate expressions and relative rates. So it's important to remember that rate expressions and relative rates are all about the rate of consumption, rate of formation, and the overall rate of the reaction, and they are all related to one another via stoichiometry. So again, this is a very important slide to come back to as you are working through homework problems. Using this slide, you should be able to work out any example problems like the ones I did in these slides here. All right, now we're going to shift gears slightly and we are going to talk about the rate law. So the rate law, it's similar to what we've just discussed, but it's got a key difference. So the rate law relates the reaction rate to the reactant concentrations. So what we were looking at before, we were just purely looking at the relative rates between the different reactants and the overall reaction itself. Now we are going to analyze how the reaction rate is related to the reactant concentrations. So suppose we have a general reaction. A plus B forms products where the little a and the little b represent the coefficients. Our generic rate law is given here, where we can say that the rate of the reaction equals K times the concentration of A to the X power times the concentration of B to the Y power. What are these variables? Well, again, this is the rate of the reaction. K here is the rate constant, and the rate constant is specific to a reaction at a given temperature. X and Y are the reaction order of A and B, respectively. So reaction order is not related to stoichiometry, but it is related to the reaction mechanism, which we will cover in the next lecture. Rate laws are experimentally determined. So there are three different reaction orders. There is first order. So if a reactant is first order, what this means is that the reactant concentration has a proportional direct effect on reaction rate, meaning if you were to double the reactant concentration, you would double the reaction rates. Next is second order. In second order, reactant concentration has a squared effect on the reaction rate, meaning if you were to double the reactant concentration, you would quadruple the reaction rates. And finally, zeroth order. In a zeroth order reactant, the reactant concentration has no effect on the reaction rate. You do not include zero order reactants in the rate law. Why is this? Think about it mathematically, and think about this rate law here. If I have something raised to the 0 power, anything raised to the 0 power is just 1, and so that reactant does not show up in the overall rate law. Now, rate laws are always determined experimentally. They are always defined in terms of the reactant, not product concentrations. The reaction order of a reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So it's important to note here that reaction order and relative rates are two different things. What we were looking at in the first half of the lecture were relative rates. So it was just comparing the rates of the reactants and the products to each other and to the overall relative rate of the reaction. Here we are comparing concentration to reaction rate. So reaction order is not related to the stoichiometric coefficient. So suppose you had a reaction F2 plus 2ClO2 forms 2FClO2. So our generic reaction, or our generic rate law would be rate reaction equals K times F2 to the X power times ClO2 to the Y power. Again, do not put the coefficients here up top. Sometimes they will match. It's possible that the coefficients will match the reaction order, but you cannot immediately assume that. You need to determine the reaction order experimentally. So the most common method you will see is something called the method of initial rates, which may be abbreviated as MIR. The method of initial rates is an experimental technique used to determine the rate law for a reaction. The reaction is run several times using different trials where we use different starting concentration of each reactant each time. The initial rate of reaction is measured for each trial, and then from this data, we're going to calculate the reaction order for each reactant. Knowing reaction orders, we can then write the rate law and then calculate the value of the rate constant K. Let me show you an example using that reaction I outlined on the previous slide. So you may be given a question like this, where you were given the balanced chemical equation and you're given a table with some data in it, and you are told to determine the rate law for this reaction using the data provided. First, you need to write your generic rate law, which I outlined previously. Now what you need to do is you're going to choose two trials, and you want to choose two trials with one of the reactants in mind. So you are going to determine the reaction order of these two reactants one at a time. You can't do both at the same time. So let's suppose I wanted to start by finding the reaction order of ClO2 first. If I want to find the reaction order for ClO2, I need to pick two trials where ClO2's concentration is different, but the other reactant's concentration is the same. So again, to repeat that, if I want to find the reaction order for ClO2, I need to choose two trials where ClO2's concentration is different in the two trials, but the other reactant's concentration is the same. So to me, that points to trials 1 and 2. Here, going from trial 1 to trial 2, ClO2's concentration quadruples, whereas F2's concentration stays the same. So because F2's concentration is staying the same, we can safely assume that any change in the rate is due to the change in concentration of ClO2. We can also should notice that as ClO2's concentration quadrupled, the initial rate quadrupled. So here then we had a 1-to-1 effect, and the reaction is therefore first order in ClO2. Next, I'm going to compare trials 1 and 3 to analyze F2. So in trial 1 versus trial 3, notice that ClO2 stays the same, whereas F2 doubled. So any change in the initial rate can be safely assumed to be due to the change in F2. So F2 doubled, the initial rate doubled. This is also a 1-to-1 effect, so the reaction is also first order in F2. Since the reaction is first order in both ClO2 and F2, the rate law is rate reaction equals K times F2 times ClO2. These exponents are both 1, and so you don't need to write them in. There are implied exponents of 1 here. So this is generally how you use the method of initial rates. Oftentimes, on example problems or homework problems that you get, the numbers are going to be more complicated than this, and it's not going to be as easy as just spotting a quadruple and a quadruple, and then we'll show you how you work through that math here, but that is the general method. All right. Let me show you another example problem. So this one states, determine the rate law and calculate the rate constant for the following reaction from the data provided. We have S2O8 2- plus 3I- forms 2SO4 2- and I3-. So here we have 3 trials with our 2 reactants. So trials 1 and 2. The first reactant stays the same. Trials 2 and 3, the second reactant stays the same, and we can see the initial rates given here. Now, as with the previous problem, you're going to want to compare the different trials of the experiment to find the reaction order for the different reactants. So I'm going to start with I-. Suppose I want to find the reaction order for I- first. I should choose 2 trials where where its concentration changes, but the other reactant, the S2O8 2- stays the same. Here, my eye is drawn to trials 1 and 2, where S2O8 2- stays the same, where I-, notice here that its concentration is double, but comparing 1 and 2. So here, going from 2 to 1, I-'s concentration doubles. Notice that the initial rate also doubles. So we could then say that I- is first order. Now, I'm going to compare trials 2 and 3, because going from trial 2 to trial 3, S2O8 2- doubles and I- stays the same. So this reactant doubles, the initial rate doubles, so S2O8 2- is also first order. After establishing that the reaction is first order in both reactants, we can write the rate law. Rate equals K times the concentration of S2O8 2- times the concentration of I-, both having exponents of 1. If you want to find the rate constant K, plug experimental data into the rate law. You can choose any of the 3 trials here, and it should work out the same. So if I plugged in trial 1, plug in 0.08 here, 0.034 here, and 2.2 times 10 to the -4th here, and solve for K. On this slide, I have shown the work for all 3 trials. Again, it doesn't matter which one you do. Typically, you should calculate it for all and take the average, since experimental error will cause actual data to vary. But oftentimes on these problems, you can just choose one of the trials and plug it in and solve for K. You should get the same value for all cases. And so here, we see that we get the same K value for all 3, 0.08088 molar -1 s seconds -1. A couple quick notes about units. The unit for the overall rate of the reaction are always molar per second. So the initial rates, this value right here, is always in molar per second. So because it's in molar per second, the units of the rate constant K depend on the reaction order. So here we have rate reaction equals K times A to the X power. So this value right here is always molar over second. So in a first order reaction, we're going to have molar over second here, and we're going to have just molar for our concentration. So K is going to have units of inverse seconds. If we have a second order reaction, so here if you have one reactant to the second power, again we have molar over second on the left side, molar squared on the right side, which means K is going to have units of inverse molar, inverse seconds. And then finally, in a zero order reaction, we have molar over second on this side. We have m to the 0 power, so this unit disappears. K is going to have units of molar over second to match the units on the left side of the equation. All right, now I'm going to walk you through a slightly more difficult problem and show you how you do the math on a problem where you need to use the method of initial rates. So this problem states, determine the rate law and calculate the rate constant for the following reaction from the data provided. 2NO plus CO2 forms 2NOCl. Here we have our three trials. So I'm going to start by setting up my generic rate law, where I say that rate equals K times NO to the X power times Cl2 to the Y power. So we can use the following formula to solve for the reaction orders of each reactant, where we say that A1 over A2 to the X power equals rate 1 over rate 2. So basically what you're doing here is you're going to take two trials and you're just going to divide the two trials by one another. So let me show you what the actual math looks like here. I'm going to start by trying to determine the rate order for NO. So I'm going to compare trials 1 and 3, because in trials 1 and 3, Cl2 stays the same. So the Cl2s will cancel each other out. So I'm going to take trial 3 and I'm going to divide by trial 1. I generally recommend putting the trial with the larger values on top. See, trial 3, we have a concentration of 0.15, and trial 1, a concentration of 0.10. So I'm going to divide trial 3 divided by trial 1. So I'm going to say then that the concentration of NO3 divided by the concentration of NO1 all to the X power is going to be equal to rate 3 over rate 1. So we can plug some values in. 0.15 plugged in here, 0.10 plugged in here, 6.75 plugged in here for rate 3, and 3.00 times 10 to the negative third plugged in here for rate 1. When you set this up, you get inside the parentheses, you get 1.50. So we have 1.50 to the X power equals 2.25. To get the X out of the exponent, you're going to want to take the natural log of both sides. So I'm going to take the natural log of 1.50 to the X power equals the natural log of 2.25. Now, using my natural log rules, I can pull the X out of the exponent and I can bring it out front. So I get X times natural log of 1.50 equals natural log of 2.25. This gives me X equals natural log of 2.25 divided by natural log of 1.50. If you plug that into your calculator, you should find that X equals 2. And so now we know then that NO is second order. Let's repeat this for Cl2. So to find the order of Cl2, I'm going to choose trials 1 and 2. Since in trials 1 and 2, NO stays the same, but Cl2 changes. So I'm going to do trial 2 over trial 1. So I'll do the concentration of Cl2 in trial 2 divided by the concentration of Cl2 in trial 1. All of that within the parentheses raised to the Y power equals rate 2 over rate 1. So let's plug our values in. Concentration of CO2 in trial 2, concentration of Cl2 in trial 1 plugged in here, and then rate 2 over rate 1. So 4.50 times 10 to the negative third divided by 3.00 times 10 to the negative third. This gives me 1.50 to the Y power equals 1.50. Because these two values are the same, we don't need to do that natural log trick, and we find then that Y equals 1. Cl2 is first order. So we found this reaction is second order in NO and first order in Cl2. Therefore, we can write the rate law. Rate equals K times NO2 squared times Cl2 to the first power. Again, you don't have to write this one here. I'm just writing it out since we had an exponent of 2. Now, to find K, simply plug experimental data into the rate law. So again, you could choose any of the trials and you should still get the same answer. I'll just use the trial 1 data. So I'll plug in 3.00 times 10 to the negative third for the initial rate. I'll plug in 0.10 for the concentration of NO and 0.10 for the concentration of Cl2 and solve for K. And you should find that K equals 3.0 molar to the negative second S to the negative first. Okay, so that's how the method of initial rate works, and that is the end of this lecture. I have 2 additional practice problems here, so if you would like, I would encourage you to pause the video now. Okay, here are the answers to those problems. That is the end of this lecture, and that is the end of this video. I hope you found this helpful. If you've got any questions, please feel free to reach out to me via email, or if you're watching this on YouTube and you're not from Wake Tech, you can comment down below or message me on YouTube, and I'll help as best as I can. I hope you have a great day, and I'll see you in the next one.